This is the exciting part of the day. We are going to have 5-minute lightning talks. They are going to be back to back to back. I am going to share my screen. So for all of our speakers today, thank you very much for submitting your slides. I'm going to be driving the slides, and unless you pre-recorded your talk, you will be able to come off mute when your talk is announced, and you will be able to speak to it. You'll notice I have this timer that will be running on the screen. I will try to move it out of the way of any content on the slides. But yeah, without further ado, our first talk is from Yifan with Lockheed Martin, and he has pre-recorded his talk, so I am just going to hit go.
Hi, my name is Yifan from the Lockheed Martin Space Advanced Technology Center, and today I want to talk about how lunar electrochemistry as a paradigm enables scalable energy storage on the lunar surface. Why do we need in-situ resource utilization, or more accurately, when do we need it? To be clear, what we're talking about is the difference between Earth launching wholesale energy.
Sorry, just a second, everyone. Sean pointed out to me that you're seeing presenter view. Let me make sure I am sharing the correct screen. Are you seeing the correct view now, Sean? Perfect.
That's right.
Thank you.
Yep.
Apologies.
Storage systems versus Earth launching an ISRU.
We are
Volume
not
has
hearing
dropped out.
audio though.
I am so sorry. That is entirely my fault. Let me restart Yifan's slides because I don't want his recording to be ruined by my incompetence. Sharing audio, you know, always a little bit questionable. Okay, let's give it another go.
Why do we need in-situ resource utilization? Hi, my name is Yifan from the Lockheed Martin Space Advanced Technology Center, and today I want to talk about how lunar electrochemistry as a paradigm enables scalable energy storage on the lunar surface. Why do we need in-situ resource utilization, or more accurately, when do we need it? To be clear, what we're talking about is the difference between Earth launching wholesale energy storage systems versus Earth launching an ISRU plant, the balance of plant elements, and then otherwise manufacturing the bulk of the batteries using materials available in situ. So for low scales of energy storage needs, it's not likely to make sense compared to Earth launching. However, I think we're entering murky areas where mission by mission, we're going to need to do the trades to figure out which strategy, Earth launching or ISRU, will make more economic sense. But here's the critical point on this graph. If you believe in the necessity to scale, for example, if you believe in a booming lunar and cislunar infrastructure supporting an X trillion-dollar future space economy, then you need the power architecture to back that up, and storage is a critical element of the power equation. We will not be able to achieve that scale of energy storage without ISRU. A solution for ISRU energy storage is going to require advances on all fronts. Now, today I want to focus on the most fundamental front, lunar electrochemistry. I'm defining lunar electrochemistry as the study of converting between electron movement and chemical reactions using lunar elements. And this has applications beyond batteries and energy storage. There's applications for life support, as well as in-space manufacturing, for example, electrodeposition. Why do we need lunar electrochemistry as opposed to just Earth electrochemistry? Well, it turns out Earth electrochemistry is built on a backbone of water and dead dinosaurs. And it turns out that on the moon, one of those is a critical resource and one of them doesn't exist. So we need to forget about this idea that we have plentiful organic solvents and additives and all of these materials that are built out of petrochemicals and fossil fuels, and rethink optimal electrochemistry for the moon using a resource-constrained space. So these next couple of slides, I'm just going to flash through a couple of examples to show ways in which we might need to rethink the problem at the fundamental level. Regenerative fuel cells are probably a bad example of this because they are the most technologically mature for space applications, and they may require the least rethinking here. Electrolyzing ISRU water to hydrogen and oxygen as a form of energy storage. At the same time, though, I think that there's still a lot of new science that needs to happen in optimizing hydrogen storage on the moon, as well as ensuring catalyst membrane and component stability. Another aqueous-based technology is the redox flow battery. Here, there's a strong reliance on organic additives and organometallics. So research really needs to show how we minimize the reliance on these chemicals, as well as minimize reliance on water by increasing the concentration of electrolytes. There's a lot of interesting work on Earth on exploring beyond lithium batteries, for example, sodium, magnesium, calcium, all of which are more Earth abundant as well as being abundant in the lunar regolith. Some of these batteries suffer ion mobility challenges, which impacts their rechargeability and delivering power. It's critical that as we explore how to address those challenges in the lunar environment, we rely less on the materials that we can't lunar source, like organic additives, and more on, for example, advanced processing techniques or nanostructure. Finally, I want to call out that over the last few decades of battery research on Earth, we've developed a diversity of architectures to suit specific end applications. And the end-use application of lunar surface energy storage is likely going to involve an architecture that's, again, completely different from anything we've developed for Earth. So let's zoom back out. If you believe in a robust, booming future space economy, you need resilient, scalable energy storage to back that up. To get there, you need lunar ISRU, and to enable ISRU energy storage, you need advances in lunar electrochemistry. It's a big problem, so how do we take steps to solve it? Well, I think it starts by calling out the problem for what it is. It's a big problem that we care about. So we need a simultaneous demand signal from the stakeholders, as well as a technology push. We also need to approach the problem using a systems approach. So instead of solving subproblems sequentially as we work up the TRL ladder, start with the systems design. Let that direct the fundamental science. Let the results of that redirect the systems design and feedback. What that means is that the teams working to solve this problem must be multifaceted by design. Small and large businesses, academic labs, national labs working in tandem to solve the same problem. Finally, let's not forget that what we're talking about here is scalable energy storage in a resource-constrained environment. We live in a resource-constrained environment and we need scalable energy storage. So conversation with the Department of Defense and the Department of Energy on aligned terrestrial applications will be critical for maturing the technology for space. I think this workshop is a great first step to that. And if you want to continue the conversation, please reach out by email and I'd be happy to talk. Thank you.
All right, thanks very much, Yifan. Next up, we have Hasnain Nisar from University of Connecticut. Hasnain, I am going to mute myself for this one, and you may unmute and just tell me next slide whenever you'd like to progress the slides.
Okay, sure, thank you. Can you, yeah. Hello, everyone. I'm Hasnain, a PhD student in the University of Connecticut. I'm working in a project with the Resilient Extraterrestrial Habitat Institute, collaborated with the Purdue University, Harvard, and University of Texas, San Antonio. Next slide, please. So today I will present our cyber physical test bed for the space microgrid that we have built in the our lab at the University of Connecticut. Next slide, please. So I will talk about a brief introduction of why we need cyber physical test bed. I will explain the our proposed architecture followed by its implementation. I will show some of the airlock scenarios and will explain all the capabilities of our test bed followed by the conclusion. Next slide, please. As we know that nowadays a growing interest in long-term space exploration and human presence in space require a power system that is reliable, resilient, and full autonomous in harsh environments. We can build a perfect power system in the simulation, but for the testing and validating its realistic behavior, a cyber physical test bed is required. Next slide, please. So this is our cyber physical test bed architecture. On the left side, we have a big and complex models of the control and management of the power. We have the nuclear, solar, and energy storage models for the microgrid developed by my colleague, Leila. She will present after me. In hardware, we have pressurized box, which represent the habitat, couple of electronic loads that represent the space habitat loads. We have the robot arm, which repaired the damage any caused to the pressure box. All these systems are communicated by a time-sensitive network. So in this project, we have 4 groups: the communication team, the robotic team, the structure health monitoring team for the pressure box, and power system team. In our test bed, we have the capabilities to validate any model, nuclear, solar energy in the hardware. We can bring from the software and implement that and validate in the hardware. Next slide, please. This is the test bed setup on the, so this is the block diagram of the power and communication system. In this case, only the solar PVs and couple of loads are in the hardware, and the rest of the system is in the cyber. And both are connected using the time sensitive networks. I will not go much into detail because of the time. So next slide, please. Yeah, so that's this is the test bed setup. On the right side, you can see we have in the rack, we have the PV simulator and few of the electronic loads that represent these habitat loads. They are powered by the power amplifier, and the rest of the system is running in the real time on the OpenRT, a real-time simulator. In the middle, we have the VFD, which supplies the power to compressor heat pad connected to pressurize to maintain the pressure and the temperature. We have a robot arm which can repair any damage to the pressure box. Next slide, please. So this is the components, sensor and control signals connections. I will not go much into detail, but I can show you, like, for example, the PV emulator. It is a DC power supply, which is acting like the PV simulator connected through the Ethernet, which receive the signal of voltage, power, and current set points from the cyber side, which is running on real time in the OpenRT. Can you go next, please? Yeah, so this is a airlock scenario in which I open the pressure valve of the pressure box to see the performance of the power system, that how it is behaving. Can you play the video or go next? Yeah, so in this, in the normal condition, the compressor was off, but once I opened the valve, the cyber system detect the leak and turn on the compressor. So in that case, how, like, we were validating how the other power system is performing. And after the cyber system sent the command to a robot for the repair. In this case, only the loads you can see on the right were in the hardware, which were powered by the PV emulator, were in the hardware, and the rest of the system was in the cyber running on the OpenRT. So now the robot is repairing, and we can see the behavior of the other system, like how they are behaving, which were simulated, which were running on the real time. Next slide, please. So our testbed has the capability to implement a virtual real-time environment that represents the space habitat system. We have the capability to validate the functionality of extraterrestrial habitat under different disturbances. We have the capability to develop microgrid solutions for long-term human presence in space. And we can do more research and innovation for the resilient and reliable power system using this testbed. Next slide, please. So
and I know this is your last one, Hasnain.
yeah, this is the last one, sorry. So by emulating the realistic condition using the cyber physical test bed, we can analyze the power system performance, access its robustness, and identify the power areas for the improvement in the power dispatch, load management, and condition monitoring. Thank you.
Thank you very much. All right, next up, we have Leila Chebbo, also from University of Connecticut. Go ahead and take it away.
Hello, everyone. Can you hear me?
Yes.
Okay, perfect. Hello, everyone. My name is Leila Chebbo. I'm a PhD student at the University of Connecticut, and I'm the Power System Modeler for RETH Institute. Today, I will be presenting our work about the power system modeling and operation for extraterrestrial habitats under environmental disturbances. Next slide, please. To start with an overview of the power system for space habitat, actually, this is considered as a microgrid because it consists of an interconnection between different types of loads and different generation units. It is controlled by a smart power distribution, and this power system is exposed to external disturbances that can affect its functionality and damage its components, which requires an agent intervention or robotic intervention to be repaired. Next slide, please. And next slide. Okay, so I'll start with the electric loads. So electric loads in extraterrestrial habitat vary in criticality and profile. Next, please. The first type is the life support. The second type is the monitoring loads. And the third type is the space, the all other loads in the space habitat, such as the scientific instruments or the housekeeping or chargers of electric vehicles and rovers. Next slide, please. So all these are modeled in profile and their profile and their criticality in our system. After that, I will go over the different technologies that are proposed for the space microgrid. Okay, so as we know, non-traditional energy generation technologies are suggested due to the extreme environment in space. And can we go next, please? And the first type is the multi-junction solar PV, and it is the main source of power for space application. The second type is the nuclear fusion or the kilopower nuclear fusion. And the third type that is proposed in the literature, but we did not include it in our architecture, is the fuel cells. We did not include this because of the limited resources in space and the low technology readiness to be sent to space. Okay, now I will talk about the energy storage. And energy storage, actually, can we go next, please? And energy storage is the only solution to support the habitat during critical situation, disturbances, or failures. And actually, for space application, we found out that the NCA lithium-based batteries are mainly used because of their capability to operate at very low temperature, and they have a long lifetime. Now let's go over the smart power distribution, which is the brain of this system. Actually, it is responsible. Can we go next? Yes. Actually, it is responsible to control, manage, and communicate between the models and the power system. And it consists of two main parts or two main models. The first one is the power dispatch and scheduling model, which is responsible to allocate the power generation. And the second part is the load prioritization and the load distribution model. Can we go next? The power distribution system for our microgrid is proposed to be DC power distribution because it has a high efficiency and reliability, and it is easy to maintain. And most importantly, the DC power distribution system is currently employed in the International Space Station. Can we go next? Okay, for the voltage levels that are proposed in this microgrid or in this distribution system, they are proposed based on the ratings of the power generation units. It is proposed based on the requirements of the load in the International Space Station and based on electrical system ratings in aeronautic applications. Can we go next? Okay, and finally, I will go over the disturbances that we have in space. So as we know, the power, can we go next, please? As we know, the system is exposed to different disturbances, and I'll list, and these are the main, which are the extreme temperature, the micrometeorite, the solar radiation, and also the habitat is exposed to other hazards, such as fires inside the interior environment. Can we go next? So all these components that I talked about are modeled in a modular space habitat model in MATLAB Simulink. And to test its functionality, can we go next? And to test its
I can go next, but I do want to let you know you're over time.
Yeah. Okay, I will summarize the work here. We ran different scenarios. We ran different scenarios to study the response of the space habitat and the effect of any damage in the power system on all the habitats. And the first scenario that we ran was a benchmark scenario where we showed that it was a day hour, so the solar power were generating and the nuclear generation also was good. And we saw that all our loads was supplied by power. In the second scenario, we introduced a meteorite with high intensity level on the nuclear reactor, and we saw that the nuclear generation decreased. However, the system was still able to maintain all the loads because we had a robotic intervention and they were working on repairing the damages we have. And in the third scenario, we added the meteorite with high dust accumulation level without any intervention of the repair. And we found out that the habitat was running without power, and the main load that was affected is the monitoring load, where our fault detection and diagnosis equipment were not sending any signal about the health status of the system. And this led to an unautomated repair.
Leila, I'm going to give you about 10 more seconds.
I'm done. I'll conclude my work. This, yeah, we can go to the last slide. So this work proposed a microgrid architecture for the space habitat, and also it addressed the non-technical and environmental challenges of the space microgrid, and it showed the effect of the external disturbances on the power system. Thank you so much. I'm sorry I went very fast, but please let me know if you have any question. I can go over them.
Thank you, Leila. Sorry to cut you off. Gotta keep it moving. All right, next we have, I'm sorry, I believe the speaker's name changed in the last second. Are we having Yash Mirchandani, or are we having someone else for
No,
Sir?
that's right. Hi, Julie. This is Yash. How are you?
Hi, excellent. Let me just get your slides up in full screen. Up in full screen. There we go.
Perfect. I think there was a slide 1.
Oh, yes. I'm sorry. There we go. I was testing.
Yeah, perfect. So hello, guys. Good afternoon. I just wanted to spend a few minutes to talk about my company, Symatec Incorporated, out of Middletown, Connecticut. We're right outside of Hartford. We're a minority woman-owned small business, and we're working on some exciting new innovative technology, which would definitely have relevant cislunar and lunar applications. Primarily, it centers around, if you could go to the next slide, please, Julie. So our core competencies are essentially using this novel ultra wide bandgap semiconductor material, which allows us to achieve unparalleled power density while also offering high frequency applications. Currently, if you look at the semiconductor space and you look at silicon and you look at some of the new exotic wide bandgap semiconductor material, including gallium nitride and silicon carbide, some of the issues that it faces is that silicon carbide, while it can handle high power density, is not radiation tolerant. A lot of the transistors and other electronics that are based on silicon carbide have premature failure, single event burnout, single event effects, and other issues that don't allow it to really be used for long purpose, long duration missions, especially if we're talking about cislunar and lunar surface power transmission and distribution systems. Gallium nitride, currently the issue there is you really can't build anything more than 600 volts. It's not as power dense as silicon carbide. So you're really limited to low power solutions. That's where we're actually very proficient and are currently building a game-changing power converter using gallium oxide, where we can offer the same benefits as silicon carbide, as well as couple that with the gallium nitride benefits of high frequency switching. So to sum it up, we're able to give you unparalleled power dense solutions with high speed switching, including radiation tolerant products that have actually been tested for both cumulative dose and single event effects. Could you go to the next slide? Obviously, there's cost implications. We are roughly at half the cost of silicon carbide and gallium nitride based devices. We're able to miniaturize pretty much any semiconductor device. And so we decided to focus primarily on transistors and MOSFETs, primarily because that's the limiting factor for power conversion based off our market analysis. And, we've worked extensively with NASA to come up with switches that are actually inherently radiation tolerant, just because of our material choice and our innovative design, which, by the way, has been patented. We're able to manipulate and repackage this material, gallium oxide, and couple it with other substrates to improve our heat rejection. One of the other benefits of our product is that it really can withstand high temperature operation in, like I said, harsh radiation environments. And that's where really, as I discussed before, we have really a niche area because of our capability to operate this material. Could you go to the next slide, please? So These are just a little technical specs on the Schottky diodes and MOSFETs that we've currently developed, tested primarily for NASA and other worldwide space customers. You'll see some of the specifications and in terms of both the single event effects as well as cumulative dose. Could you go to the next slide, please? Again, as I mentioned before, we're actively working on a power converter for long distance power transmission, primarily geared towards lunar surface applications, but also for LEO, GEO, electric power systems for both CubeSats and larger platforms. These products are currently being tested and qualified to the MIL standards that are listed on this website or on this slide deck. Additionally, we've got a lot of interest from DoD stakeholders as well for power transmission systems here on Earth, as well as fast power charging for some of their heavy duty platforms. And we're actively working with them right now to qualify this product. Could you go to the next slide? Oh, I think that's it. Perfect. So I'm right before time. Thank you.
Excellent. Thank you so much. All right. Yeah, look at that. You got under 5 minutes. All right. Next up, we have Ayan Mallik from the Arizona State University, and I will give you actual 5 minutes on your timer. Make you full screen. And Ayan, take it away.
Okay, thank you. Thanks, Julie, for the introduction. It's my pleasure to be here in such an interesting session to present a part of our research on control of multi-port power converters for space applications. This research, as a matter of fact, has been conducted as part of a NASA SBIR program that is a collaborative effort between Arizona State University and Coolcat Electronics that is based in Maryland and has expertise in designing and fabricating different wide bandgap silicon carbide semiconductors. So on behalf of ASU, as you see on the slide, Saikat Dey is my PhD student who worked on this project, and I'm the faculty advisor. Next slide, please. Well, so with the emerging power and energy needs in the ongoing and upcoming space missions, the demand for multi-port power conversion systems to meet different types of energy management needs is omnipresent, as you know. Moreover, the next generation power conversion systems are expected to address the integration of various energy storage and source ports in a single integrated, efficient, reliable, and high density manner to make the space missions more sustainable and cost effective. To this context, this particular problem statement can be solved by using multiple dual active bridge converters placed between the respective source and the load ports. But the problem is that with this solution, the usage of multiple bulky transformer or other magnetic components increases the weight and volume and regrets the conversion efficiency of the whole system. So therefore, like in this particular scenario, we propose something called multi-active bridge, in short MAB converters, that are deemed as promising solutions to enable multi-directional power conversion over a wide range of voltage gain and loading conditions. But the problem with this particular approach is that at corner conditions, these conventional MAB circuits encounter very high RMS currents and also loss of soft switching that leads to efficiency degradation. So we propose an advanced approach to take care of this particular issue by involving hybrid, we call it hybrid phase duty frequency modulation, that takes care of like loss minimization at these corner conditions, and also like implementation of different optimal control schemes. And we propose something called a feed-forward neural network approach, like an AI-driven approach to address these existing issues. Next, please. So here we show a standard schematic for TAB, triple active bridge converter, that couples the solar PV with the localized energy storage and DC microgrid. The PV panel string is rated for 160 volts utilizing Coolcat silicon carbide devices. And the DC microgrid is of 120 volts and the energy storage is of 28 volts utilizing GaN, like gallium nitride devices for switching. In this case, the output voltages and the power transfer could be controlled by utilizing the phase shift variables between the full bridges, and the duty cycles are basically involved in further optimization of certain objective functions such as the loss, RMS currents, ZV as a region, etc. Next slide, please. Okay, so here we are showing a brief schematic of the proposed feed-forward neural network architecture that presents a data-driven solution for optimal synthesis of the control parameters. This particular network consists of one input layer, two hidden layers, and one output layer. The network inputs would be like the operating condition parameters, such as your converter load resistances, output voltage references, and also the circuit parameters that could be subject to uncertainty. And what we're doing is that like the output of this network is going to be generating the control variables, as well as provide an estimation of the system parameters that could be subject to uncertainty. And those estimated circuit parameters are again fed back to the network as inputs in the next execution cycle. So in this case, what we're doing is we are exhibiting the converter level control in the DSP, and the feed-forward neural network, this machine learning algorithm, is run in the FPGA as a side channel kind of operation, while we like establish some sort of inter-controller communication for data exchange. And these AI methods are like much superior compared to conventional lookup table based approach that is deemed as a very memory intensive solution with a higher space complexity. Next slide, please. We show some experimental results taken from the hardware, highlighting some comparisons between the conventional dual phase shift and proposed pentaphase shift modulation schemes. We show that using this particular neural network approach, we achieve 1.8% higher efficiency than the conventional approach due to gaining more control flexibility in different types of minimization of different objective functions. Next slide, please. So here we're demonstrating the operation of like the converter under different load transient scenarios. It's evident from the waveforms that the converter is transitioning to the most optimal switching modulation scheme if required once the load change happens at any of the output ports. And this optimization routine improves the efficiency by like around 3% compared to the basic modulation scheme. So in summary, I can state that we showed that this particular neural network scheme could be a very feasible approach moving forward to account for such control variable optimization that is sort of accountable for maximum efficiency tracking regardless of any circuit parametric uncertainty. So with that, I'd like to conclude the presentation. It will be open to questions over the chat, and you can also drop me an email with your questions. Thank you.
Thank you very much. And thank you for wrapping that up. Appreciate it. Next up, sorry, not that one. We have Ibrahim Bardak from Bastion Technologies, and I will go ahead and make this big. Reset the timer. And Ibrahim, you can take it away.
Hello, everyone. So yeah, I think Jeff is there. He wanted to do the introduction, but if Jeff is not listening, maybe I can proceed with the slides. Jeff, are you there? Oh, okay. So he's not there. So okay, sorry again. Yeah, my name is Ibrahim Bardak, and I work actually at the GP and NASA, and also Bastion Technology as a contractor. So I'll be presenting or talking about the EMI lightning-induced transient susceptibility, and I will focus mainly in the Y458. Next slide, please. Okay, so that's so our introduction. Basically, it's just like what we can really offer in the in the field of reliability when it comes to EMI AMC. Electromagnetic interference can potentially be generated by switching sources like DC-DC converters, and that can really reach the power and signal lines and adversely affect communication and other sensitive devices. So, in order to prevent and minimize EMI to acceptable level, so grounding, schematic design, layout, filtering, and shielding must be established at the earliest point of the design. And also this is include like optimization of a general AMC victim source matrix for the purpose of down selecting designs to undergo EMI AMC early risk reduction analysis, and to ensure that the initial design is done accurately with EMI containment in mind, which will guarantee the project success down the road. Next slide, please. So, okay, so the topic today of lightning really, and everybody knows lightning strikes have the potential to create calamity. So therefore, equipment and their critical systems require robust and reliable designs and stringent verification testing that meet all the applicable standards and regulations, and mainly DO-160, which I'm gonna talk a little bit about in the next slides. So yeah, so systems require robust and reliable design that must be implemented to ensure that they will withstand the effects of the lightning. And also, it is imperative that systems continue to perform as required and designed. So this is what that's combination of reliability and also resilience. So, and in order to meet the lightning stringent requirements, again, grounding, schematic design, layouts, design, filtering, and shielding must be established at the earliest point in the project. And for testing or verifications, basically there are two groups of tests that may be used for qualifications according to the RTC DO-160. So the first is a damage tolerance test performed using pin injection, which is really involved the injection of transient directly into the EUT interface circuits. And the second group, it's evaluate the functional upset tolerance of the equipment under test when transients are applied to interconnecting cable bundles. So, and all these things are detailed in the DO-160 section 22 and 23. Next slide, please. So the focus in this workshop, again, as I mentioned, is waveform 5A. And the reason I'm focusing on this one, because this is one of the most stringent indirect strikes. And basically this waveform is applicable, to equipment composed of metal framework and mainly that like carbon fiber composite structure, which they are not good conductors. So the conductivity is really not very low with this type of structure. So pin injection testing basically is gonna be used for really assessing the dielectric withstand voltage or damage tolerance of the equipment interface circuit. And at this point, so the equipment manufacturer must test the level at waveforms consistent with expected use and the way it's going to be installed. So, and if it's not tested, it can create really a huge chaos. So next slide, please. Yeah. So, okay, this is the waveform and level. You can see that waveform, it's really like a double exponential waveform. And it's like around 10 kilohertz. And this can go up to 1600 volts, 1600 amp, which is like 1 ohm impedance, which is so stringent. Next slide, please. So basically, there is a requirement when performing this lightning insulation test. So basically, it's driven by what we call the impedance modulus Z between the conductor and the equipment casing over a specific frequency range that should be determined really during when we're defining the requirement for lightning. That frequency should be defined, and that impedance modulus Z should be also defined. And the key parameter to control here is really C, is the total capacitance of chassis. And that total capacitance of chassis includes parasitics capacitance and also any capacitance that there can be used for filtering common mode noise, which is mainly we call them Y capacitors from really the inputs of the power lines to chassis. And that if that capacitance is very high, that can create a lot of problem. And that's what really this waveform, this lightning, and find that capacitance as a favorable path to wreak havoc in the air.
Ibrahim, just a heads up, you are over time, so please wrap it up.
Okay, so yeah, next slide, please. So, so the summary. So basically, planned lunar mission offer a unique opportunity to expand our knowledge and capabilities with respect to complex engineering system in harsh environments. So an attention should be given to engineering requirements, interfaces, and verification, as it was called by RIV, with emphasis on EMI, MC design, testing, and troubleshooting. And the driver requirements are found in the following: NASA tailored requirement, technical handbooks, military standards, and also the RTC DO.
Ibrahim, I'm going to go ahead and break in because we've got all these written down. So thank you. But thank you very much. We do need to keep it moving along. Oh, you have a nice thank you slide. Do need to keep it moving along because we have a lot more talks to get to today. Next up, we have Gary Barnhard from XISP. Gary, I will go ahead and get this up and you can take it away.
Great. Yes, I'm Gary Barnhard, and my talk today is on the lunar surface power system reliability considerations in our work on something we call space squared. Next, please. Please advance. In terms of reliability considerations, what we're dealing with really has to be end-to-end systems of systems that include both power generation, storage, transmission, distribution, and control. Our power systems are critically dependent on ancillary services, which are essential for the management, operations, and control architecture applications. And the efficient delivery of power and ancillary services is a complex systems engineering and economics problem. In terms of for lunar applications, we need systems that are scalable from to serve loads that are less than a watt to an aggregate approaching gigawatts. We require ancillary services for near real-time control. We need to meet actual customer requirements. What we field needs to make economic sense for both the venue and the applications used. We need we are required to reduce the systems engineering to practice in order to have fieldable systems. We need to be interoperable and maintainable both by robotics and EVA. We need to have layered control and support multiple failure tolerance. And we must survive in the operational environment indefinitely with periodic maintenance. Next, please. Yes. In terms of the system's requirements, we need to be able to looking at how we can reduce and reallocate systems complexity, mass, and volume, typically involving a variety of plug-in and plug-out technologies. We need to provide for dispatchable energy transfer so that we can alter the cadence of mission operations as appropriate. Reduce, eliminate, and deconflict different requirements across the end-to-end systems. We need to provide for the necessary ancillary services, better manage the environmental interfaces, enable more practical electromechanical interfaces, and foster the identification and effective use of the different synergies. And in particular, it's really a combined power and thermal problem. Next slide, please. In terms of framing the problem space, we need to meet the needs of the present as well as serve as building blocks for the next increment. The construction of the evolving increments, I think, needs to be an intrinsic part of the mission infrastructure. And it's critical to determine what are these increments of scalable, interoperable modular power and ancillary services. And, again, focusing on the fact that the solution space requires end-to-end systems, and that we need to be looking at how it is that we're retiring in buying down space, but, buying down, both real and perceived risks associated with the same. And, anything that's fielded should be scalable to at least the next increment. Next slide, please. Our space squared system really is looking at addressing the fact that fieldable lunar surface power systems haven't yet been proven tractable. We need to be able to support what amounts to being dynamic systems of system state models that support the synergistic, predictive, analytical control environment, what we call space squared, to be able to provide a framework for abstracting and integrating all the available qualitative and quantitative data. Next slide, please. What we're working on is an open source instance of a management operations control architecture application that addresses the end-to-end system. Next slide, please. And you can have an opportunity to read through this at your leisure. But the point is that it has to not just be able to be correlated to the existing data, but have a predictive and analytical control capabilities associated with the same. Next slide, please. The resulting near real-time state models end up being also surfacing not just through the conceptual and preliminary and detailed design, but through the actual control of the systems that are involved. That's our intention, and to provide a computational practical framework for the same. And it also provides an ability to deal with not just established situations, but emergent situations, which are critical for not only normal operations, but for implementing failure tolerance. And, conceptually, this is the sort of the notional view of it, in terms of where we're heading.
You are at 0,
Yeah.
and I also
Okay.
plugged the timer, so you get a couple
Right.
seconds to wrap up.
All right. So, and where this fits in, go to the next slide, please. And the next one. This is the overall problem space that we're dealing with, in the potential solution space, and our work fits on how you deal with all of the internal and external interfaces associated with the same. Appreciate the introduction. The full talk is available, through the LSIC documentation. Thank you.
Thank you so much, Gary. And last but not least, we have Jaclyn Wiley from Zeno Power. Jaclyn, I'm going to do the timer correctly this time, and you can go ahead and take it away.
All right, good morning. I'm Jaclyn Wiley. I'm speaking to you today for Zeno Power, and today I'll be briefly speaking on radioisotope power systems, RPSs, and how they fit into the evolving lunar power ecosystem. So RPSs have a very long history in exploration and have been utilized on over 85 space missions overall and 15 lunar missions. We use these systems because they're very reliable and they can be used in deep space regardless of solar irradiation. So you can say you stick them where the sun doesn't shine. All of these systems, however, in the past have been owned and operated by governments. This is partially due to the very high cost of these technologies, as well as the extremely limited access to fuel materials previously used, which included uranium, polonium, and plutonium, specifically plutonium-238, which has been used in all RPS missions in the last 30 years. Recent developments, however, in materials—
Jaclyn, I just want to remind you to let me know if you want me to progress the slides. No. I've left it here for now.
I will. Thank you.
Okay, thank you.
Recent developments in materials, launch safety, and safety technologies in general have encouraged new entrants in the nuclear space arena, including commercial actors like Zeno Power. Next chart, please. So Zeno Power is an American company developing low-cost, commercially available RPS systems. By 2026, we plan to offer both radioisotope heater units, RUs, and radioisotope thermoelectric generators, RTGs. The radioisotopes that we plan to use are much more accessible than traditional sources. Those radioisotopes include strontium-90, and now that I'm allowed to tell you, as of our tipping point award earlier this week, americium. As I said, these radioisotopes are far more accessible than the traditional sources. And the traditional sources, the high-powered isotopes like plutonium, are generated by the US government for commercial or for NASA missions at this time. And their existing supply has already been bookmarked for flagship missions like Dragonfly. And Zeno Power is not just a paper company. We have a development award from the Space Force for the first strontium-90 heat source to be developed in nearly 40 years, which will be used to support a commercial satellite mission called Lens 1, as well as I said earlier, a tipping point award from NASA to develop a universal americium-241 radioisotope power supply for use in the Artemis program. So not only are we developing the technology, however, we are also developing the regulatory and integration technology and know-how to enable a safe, legal, and successful launch, hopefully. So next chart, please. Why radioisotope power systems, and why Zeno specifically? Our value proposition is that RPS systems for both heating and for power can enable spacecraft to survive the lunar night. So we enable spacecraft to survive long-term in the short term, so to speak. So while all of our other peers on this lovely panel, or in this event, as well as in the larger space industry, are developing their longer term solutions, an RPS system can be utilized. As I said, our first system is planned to work in 2026. And these systems, which can survive the lunar night enable longer mission profiles. So these spacecraft can survive multiple lunar day-night cycles and enable the providing of services to other spacecraft. So this can include radio navigation support, so providing position navigation and timing support on the lunar surface, as well as a number of other missions, including ISRU. So you'll see on the chart, which is completely illustrative, not regarding actual data at this point in time, you'll see that the red radioisotope power line provides steady long-term power, and while it might not reach the high level of power provided by a traditional power system like solar or chemical batteries, it does last a lot longer. So next chart, please. So why Zeno? As I said, we're using materials that are already readily available. We are utilizing technology that can be available in the short term and will enable long-term missions. And those missions can be commercial rather than just being reserved for NASA missions. Though to any of our NASA compatriots on this call, we can also provide them to government sources as well. So
Jaclyn,
see
you are
on
at
our-
time. Just
Oh,
a warning.
great,
Wrap it up
perfect.
when you get a chance, please.
Thank you for coming out today. If you wish to reach out to anyone at Zeno Power, please do so. And thank you for your time.
Awesome. Thank you so much. That will conclude our lightning talks. So all of our 5-minute speakers, amazing job. Thank you so much. We're just a little bit over schedule. I am going to pass it off now to Joe to run the next set of talks, but I did want to mention for anybody who just gave a talk or anyone who had questions in the audience, you can use the Q&A feature in the webinar to address those. And of course, if you have questions for our speakers later, you can reach out to them through various avenues.